Hi guys, on this section, we're going to get started in chapter 5. We're going to start with 5.1. This is probably going to be like 2 parts, probably. So the first thing that we're going to talk about, this chapter deals with probability. And so the first thing we're going to start off is just some basic ideas and basic concepts within probability. So a probability experiment is one in which we do not know what the actual outcome will be, but we do know how a long series will come out. So for example, if we flip a coin, we don't know whether or not it's going to come up heads or tails. If we roll a die, we don't know whether or not it'll come out 1, 2, 3, 4, 5, 6. We don't know what the actual value is going to come up for each individual toss or roll of the die. However, we do know that if a coin is fair, meaning that it's not weighted to one side or the other, that we expect or we should see that about half the time or half the number of times we flip, it should come out to be heads, and the other half of the time it should be tails. So the probability of an event is the proportion of times that that thing happens in the long run, okay? So for a fair coin, again, a coin that is not weighted, we would say that it's equally likely or just as likely for heads to come up as tails, which means 1/2 of the time it will be heads, so the probability of heads is half, and the probability of tails is also going to be 1/2. So now, there is this idea thing called the law of large numbers. And so basically this says, as stuff is done over and over and over and over and over again, the proportion of the outcomes will settle into the actual proportion. So for example, if I if I toss a coin, say 10 times, I don't think it odd or anything like that if I got 7 heads out of 10. I wouldn't necessarily think that odd. But then after I've tossed it 100 times, I might have that it's come up heads 45 times. And so then if I toss it 1,000 times, maybe I have that it's 525. And then I toss it 10,000 times, I've had 5,112. Okay. So even though I fluctuated from like 7 out of 10 to 45 out of 100 to 525 out of 1,000, whatever, I'm now starting that proportion or that percentage or even that decimal is now starting to settle into that what we would expect to be half or 0.5 as we go along. Okay. So now in a probability model, there will be several outcomes. When you roll a die, there's this thing called a sample space, and knowing what the sample space is important for us because it helps us find probabilities. So for a sample space, they're going to use these braces, okay? And this is a list of every possible thing that could come out. So for a die, it would be 1, 2, 3, 4, 5, 6. For a coin, it would be heads, tails, okay? If I had marbles in a bag, it would be the colors of the marbles that are in the bag, okay? And an event is now just a grouping of items out of that set. So it could be roll an odd number, which would be 1, 3, 5, excuse me, or roll an even number, 2, 4, 6. Roll a number less than 4, 1, 2, 3, okay? So we have also what's called a probability model. And this is where it's going to look, usually we generally use a table for this. And we will list our sample space items on the left-hand side, and then we list their probability on the right-hand side, okay? Now, the other thing is for probability, we use this notation. It looks very much like function notation from algebra. Your like F of 4 type of notation, except this time we use P, a capital P for probability. And then in parentheses, we will either put the event name, as here they indicate event A, or we may even just write like they did here, probability of heads, okay? So now, there's a couple of rules for probability. We have that the probability of an event is always going to be between 0 and 1 inclusively. Inclusively here means that it could be 0 and it could be 1. If a probability of 0, then it's never going to happen, okay? And then if a probability has a value of 1, then it is guaranteed to happen. It's always going to happen. Okay? So, and everything else is sit in between. So if somebody says, oh, the probability of that is 1.25, that's wrong. It can't happen that way. Okay. So then when we talk about probabilities with equally likely outcomes, guys, this is our traditional probability that we're used to doing all the time. You're going to take the number of things that can happen and put it over the total number of things that are in the space. Okay, they talk here about the lottery with winning numbers between 0, 0, 0, 0 and 9, 9, 9, 9. Guys, that is 10,000 values, okay? We can sit there and count 1, 2, 3, 4 and get all the way up to 9,999, and that 0, 0, 0, 0 one acts as our 10,000th item. So it asks, what is the outcome that all 4 digits are the same? So you have 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, all the way up to 9, 9, 9, 9. There are 10 of those. So I would do 10 out of 10,000. In decimal, that is 0.001. So I'm going to now switch over. We're going to look at a few example problems out of the worksheets. Remember, the worksheets are available to you in the modules section. Okay. So our first one here asks us, assume that a fair die is rolled. The sample space is 1, 2, 3, 4, 5, 6. They and all outcomes are equally likely. They asked us to find P of 0. Okay, because there are no zeros in this list, so that's 0 out of 6. So I have a 0% chance. Okay? Now the next one, still in the same setup, asks us to find the probability of getting a 4. There is 1 4 in the list. We also know there's only 1 4 on a die, so that's 1 out of 6, which can be left that way. The decimal is 1.6 repeating. They do ask us generally to keep things as accurate as possible. So they're probably going to say something like, leave things in fraction format if possible, reduced fraction as well, okay? Then they ask, find the probability of less than 3. So looking at my numbers that are less than 3, I have values 2 and 1. So there are 2 sides out of 6. That will reduce to 3. Okay. Okay. Now, looking at the next one. Okay. It says, assume that a coin is tossed twice, the coin may not be fair. Now, first off, let's talk about what that sample space would be. I know it lists it, but let's talk about it, okay? My coins could come up heads, heads. The first one could come up heads, the second one could come up tails. The first one comes up tails, the second one comes up heads, or they both come up tails. That's what my sample space would look like for this, okay? Now, they are going to ask us if this represents a probability model. The answer is no. This is fine. This is fine. It's between 0 and 1. This is fine. It's between 0 and 1. This is fine. It's between 0 and 1. This is bad. Okay. It's not between 0 and 1. So that cannot be. So if this cannot be a probability space or a probability model, because not everything sits between 0 and 1. There'll be a couple other rules that we have with this a little bit later on. Okay. Now, next one, it says, in a survey of 500 likely voters in a certain city, 295 of them said that they planned to vote to re-elect the incumbent mayor. What is the probability that a surveyed voter plans to re-elect the mayor? Okay, well, they said there were 295 that would out of 500. We can clean this up. Now, helpful hint, if you have one of the TI-84s, okay, calculators, let's see if I've got one. Okay, on your calculator, okay, you can put in, okay, I can do the 295 divided by 500. And first off, I do get that that is 0.59. Okay. Now, what I'm going to hit here, I'm going to hit the math button. And then I'm going to hit enter twice. And what that's going to do is it's going to take my answer and turn it into a fraction. This fraction is now in reduced form in lowest terms. So that is 59 out of 100. Okay. So part B says interpret the results by estimating the percentage. Guys, if you've got it in decimal form, just do that double bump. So this would be 59%. Okay. And then it says if there are 47,000 eligible voters and every eligible voter votes, approximately how many voters will re-elect? We saw this one with when we did the empirical rule with the babies. You're just going to take this decimal times the total number. And we've got 27,730 would vote for that, vote for the incumbent mayor. Okay. So we'll look at one more example for this. Okay. So it says in a section of exam contains 3 true false questions. A completed exam paper is selected at random and three answers are recorded. Assuming the outcomes are equally likely, find the probability that they're all the same answer. Okay. Now, first off, I'm going to show you something that can help you on things like this, that will help you organize thoughts. Okay. This is what's called a tree diagram. And sometimes they're built kind of downwards. Mine tend to go sideways. So the concept here is on the first question, you put how many options there are. So in this case, I only have 2. So I have true or false. Okay. And then from the first question, so this was question 1. When I go to question 2, I put how many options there are for it. Now, that second question, okay, I could coming off first one, and then I'm going to do the same thing when I move out to question 3. Okay. Now, first off, I can count the number of values out here on the outside edge. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 outcomes. Okay. That means the bottom of any probability that I would do would have a value of 8. Okay. I can also figure out what these are. I generally tend to read backwards. Okay. I also write them backwards. So true, 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 false, true, true. Again, I'm reading backwards. True, false, true, false, false, true, 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 false, false, true, false, true, false, false, and false, false, false. Okay. So this would now be my sample space. Okay. There are still 1, 2, 3, 4, 5, 6, 7, 8 values there. Okay. They're going to happen. They now ask, what's the probability that all the answers are the same? Well, there's only 2 up here. I have the true, 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 and the false, false, false. Okay. That are going to be the same. So that's going to be 2 out of 8, which can be reduced down to 1/4 or 0.25 in its decimal. Okay. Now, Now they ask for the probability of exactly 2 falses. Okay, so if I take a look, I'm going to get rid of my dots over here. That has done 1, 1. There's one that has 2 in it, 1. That one has 2. That one has 2. That one has 3. They said exactly for this one. Okay, so we've got to make sure that we read carefully. That is 3 out of 8. That won't go anywhere as far as reducing, so that's 0.375. Okay. And then they ask, what's the probability that the first answer is true? Okay, so we'll mark these. First one's true, first one's true, first one's true, first one's true. First one, all those is false. So that is 4 out of 8, which will reduce to 1/2, or 0.5. Okay. And again, generally you'll have the option to write your answer in either decimal, percent, or fraction. That becomes your choice.